These videos are not intended to replace formal academic courses. Instead, they serve as a platform for knowledge sharing, offering a simplified overview of the field of applied artificial intelligence. A basic understanding of Python programming is recommended. Greetings, Assalamu alaikum, bonjour. Welcome to my first video on applied artificial intelligence. Introducing myself. My name is Walid Amara. I'm an AI solutions consultant for Majal Berkane, engaged in research and development within Innovation Lab. I, alongside my colleagues, have published 2 articles in a renowned conference. Therefore, consider me as your friendly research engineer, eager to share knowledge and make complex subjects easily consumable. These videos are in partnership with Majal Berkane for Innovation and Territorial Intelligence. References will be found in the description. Advanced AI powers technologies in the likes of ChatGPT, Tesla Autopilot, Midjourney 2, DALL-E 3, and leading weather forecasting systems. More specifically, all these systems rely on deep learning-based artificial intelligence. First and foremost, what is AI exactly? AI is the simulation of human intelligence. Basically, it's robots, computers, or machines in general being able to do human tasks and display some sort of human-like intelligence, if not better. Inside artificial intelligence is a subfield called machine learning, which is also a branch of computer science that focuses on the use of data and algorithms to imitate the way that humans learn, gradually improving its accuracy. Emphasis on the term learn because that's what makes the difference between a conventional algorithm that is made to automate or solve a specific task and a machine learning algorithm that's been designed to solve the same task. However, in this case, even though the machine learning algorithm will start off performing worse at that task in comparison to the conventional algorithm, over time, the learning aspect of machine learning will make it better and better until it outperforms the conventional one. Deep inside the machine learning field, there is also a subfield called deep learning. This field is dominated by artificial neural networks. They can solve complex and advanced problems and are today's subject. Artificial neural networks, or neural networks for short, the term is abstracted from neuroscience. It's our brain's network of neurons. Our human brains are a network of neurons that communicate through electric signals. Depending on the strength of the signal, the neurons can either fire or stay turned off. Artificial neural networks are so different from their biological counterparts, yet very similar in terms of the previously mentioned functionalities. An artificial neural network, or ANN, comprises 3 layers. The input layer, where we get the input data, the hidden layer or layers, where most of the heavy computation is done, and the output layer that has the final predictions. The ANN can perform many tasks, and these tasks, in general, fall under 5 categories. Regression tasks. In regression tasks, an ANN predicts a numerical continuous value. Imagine trying to guess the price of a house, predict inflation rates, or estimate the speed of a moving object. These are examples where the output is not categorized like yes or no, but rather a continuous number. Binary classification is a frequent job for an ANN. It involves predicting an outcome that can be just one of 2 possibilities, like predicting if an email is spam or not spam, whether a light switch is on or off, or determining if a product is good or bad. It simplifies complex decisions into a straightforward choice between 2 options. In multi-label classification, it's about predicting multiple labels for just a single input. For instance, if you're classifying images, an ANN might identify both cat, outdoor scene, and grass in the same picture. It's about assigning more than just one category to the input. Multi-classification is a task in which the input can be classified into more than 2 classes. For example, training a neural network to classify animals into multiple classes. It could be cats or dogs or birds or any other type of class. Clustering tasks involve grouping similar items together. Instead of predicting predefined categories, the ANN organizes data based on inherent similarities. An example is grouping customers with similar purchasing behavior, helping businesses tailor their marketing strategies. Anomaly detection tasks identify unusual patterns or outliers in the data. It's like spotting a fraudulent transaction in a sea of other legitimate ones, or detecting a malfunctioning machine on a production line or an airplane. The ANN helps in pinpointing deviations from the norm. Inference is the sum of all the computing operations that our neural network conducts to get the resulting output. The input layer takes the required input to perform the task. Each input is fed into a separate neuron. We can make some transformations on the values of these inputs before we begin, like transforming the temperature from Fahrenheit to Celsius or minutes to seconds. Now, each neuron is connected to one or a set of neurons. Those connections are represented as weights, which are numerical values usually within the range of 0 to 1, -1 to 1, or -0.5 to 0.5. Also, apart from the input layer's neurons, each neuron has a bias, which is a numerical value as well, that usually falls under a scale that's close to 0, or to 1, or to -1. Let's consider this random neuron in the second layer of the hidden layers. To compute its value, we examine the left connections it's associated with. The value of each connected neuron is multiplied by its corresponding weight. We sum these multiplications and then add the neuron's bias. Furthermore, we apply an activation function to the resultant sum. The activation function is, as their name suggests, are responsible for either activating the neuron or turning it off. Some common activation functions in ANNs are sigmoid or ReLU, and the output of the activation function is the value of that neuron. Congratulations, you have calculated a neuron's value. This same process is done to all the neurons on our artificial neural network. After calculating all the values within the neural network, we progress to the output layer. In a classification problem, each neuron's value in the output layer represents probabilities, with the sum of these probabilities equaling to 1. Achieving this can be enforced by using a sigmoid activation function. For regression problems, the output is represented as values denoting the predicted value, and an activation function is not mandatory. In the context of multi-label classification tasks, values can be represented as independent probabilities, and a probability distribution may be employed as well. The values of the outputs can be altered depending on the type of task that we want our ANN to accomplish. During training, we provide the ANN with the necessary data containing input values and their corresponding ground truth outputs. Following the computational process explained earlier, the predicted values are then compared to the ground truth values using a loss function. The function works as an indicator or a meter into how bad our model is performing. We use the results provided by the loss function to alter the weights of the connections and the biases of the neurons in the goal of minimizing the loss function. The loss function's formula changes depending on the task type. This adjustment occurs through the application of gradient descent, a minimization algorithm that alters parameters based on a defined learning rate to find an optimal set of values to minimize the loss function. The gradient descent algorithm, in its mathematical nature, is a minimization algorithm that considers the parameters and the defined learning rate in the goal of finding the local minima. However, this fact means that it can propose a set of parameters that is not globally optimal for this task, only locally optimal. It needs to escape the local minima. That's why we use an adaptive learning rate or regularization techniques like the L1 and L2. The gradient descent is constantly searching for the best set of weights and biases that are changed within each iteration. Each iteration has a forward propagation where our ANN receives the input values, conducts the inference, then the outputs are compared to the ground truth values using the loss function, see how our ANN is performing, then it goes back in the back propagation where it alters or refines the weights and biases according to gradient descent. This training operation is concluded following a termination criteria, which can be set by a defined number of iterations, gradient descent conversions, or achieving a certain level of accuracy where the loss becomes negligible. After determination, we proceed to test our model using a test set. The test set has data that the model has never seen before, making it a great way to see if our ANN will generalize on new data. In this example, we'll delve into the creation of an artificial neural network designed to determine the quality of coffee, an application that falls under the binary classification, one of the fundamental tasks an ANN can excel at. For simplicity, let's imagine our ANN has only two inputs: the duration our coffee has been brewed, measured in minutes, and the cooking temperature, expressed in Celsius. The objective is to predict whether the coffee quality is good or bad. Our ANN will produce two outputs. The first output neuron signifies good coffee, while the second denotes bad coffee. And since this is a binary classification problem, we'll apply a softmax activation function to the values of the neurons in the output layer, while in the hidden layer, we'll use a ReLU activation. The input layer should stay intact, without using any kind of activation, as the norm suggests. To guide the training process effectively, we'll employ a specific loss function tailored for binary classification. Let's assume that we have already gathered the necessary data for training, which are some recorded brewing times and temperatures and their corresponding coffee quality assessments. The suggested ANN architecture incorporates two hidden layers. Throughout each iteration, which involves forward propagation, where computations are executed, or inference, the resulting outputs are compared to the ground truth values using the designed loss function. Subsequently, in the back propagation phase, adjustments to the weights and biases are made based on the computed gradients, aiming to enhance performance in the subsequent iteration. The extent of adjustments to the weights and biases is determined by the employed gradient descent algorithm. It seeks the optimal set of parameters to minimize the loss function. Upon reaching convergence, which is determination criteria, we conclude the training phase, having successfully equipped our ANN for the task of coffee quality assurance. So, as a conclusion, we decided which type of task this is, a binary classification task. Then we proposed an ANN architecture that's effective for this task, and a loss function that will determine how bad our ANN is doing while training. Thirdly, we formed a dataset for our ANN to learn. Then we initialized the training for our ANN. We set a stopping criteria for training, which is the convergence of gradient descent, basically meaning that our gradient descent has failed to propose a better set of weights and biases for multiple iterations, and training it more will more than likely be futile. Now we can finally use our coffee quality assurance artificial neural network. To use it, we first brew the coffee, count the temperature and time of brewing, feed it to the ANN. The ANN will in turn respond by outputting a probability distribution. We take the greatest value between the two outputs, and that value is the final assessment of our nicely made coffee. As we bring this video to a close, I appreciate your time and engagement. I will be shortly uploading the Arabic version of this video onto this channel. For the next episode, we'll dive onto the practical implementations of ANNs in Python, PyTorch. If you found this content valuable, please show your support by liking, subscribing, and commenting on any thoughts or questions you may have. Feel free to share this video with others who might benefit from it. For more updates, you can explore my LinkedIn profile and connect with Majal Berkane on LinkedIn as well, or visit our website at BerkaneWeCan. All relevant links are available in the description below. Wishing you the best on your learning journey.